Hi and welcome to a lesson of multivariable calculus. So in today's class, we are going to learn how to find the directional derivatives of functions. So here is the theorem that says if a function f is differentiable, then f has a directional derivative in the direction of any unit vector u equals to u1i plus u2j. So it's a vector in some direction, it's a unit vector. Now let us understand what does it mean. For instance, suppose that we have a metal plate that is both in x and y direction, and we are interested in finding the temperature. So we say that the temperature is a function of x and y, right? So if we heat this end with some heating source, so we know that heat flows from higher concentration to lower concentration. It means that heat will start flowing in different directions, right? Heat will start flowing in different directions. Now if we find partial f over partial x, we know that we are finding the rate of change in the x direction. And if we find the partial f over partial y, we are finding the rate of change in the y direction. But what if we are concerned in finding this rate of change in any other direction, right? Now this embarks the sense of directional derivative. So for the computation of directional derivative, we have this notion that is du f of xy equals partial of function with respect to x at the point xy plus partial of the function with respect to y at the point xy dotted with u2. So this way we can get the directional derivative of the function, right? Now let us do some example to understand. Now let's say if we have a function that is given in this example, that is f of xy equals 4 minus 2x squared minus y squared. So the function is given, it's a function of two variables. So we have two independent variables, that is x and y. Now we need to find the directional derivative in the direction at this point 1, 1, at this point 1, 1 in the direction of a unit vector that makes an angle pi by 3 radians with the positive x-axis, right? So we are given with the point. So at this point we need to find the directional derivative, that is 1, 1, and we are also given the unit vector that makes angle pi by 3 radians. So the vector that is given is the unit vector. It makes the angle theta, let's say it's pi over 3. So now first thing we need to do is to find the gradient of this function. Now to find the gradient, we need to compute the partial derivatives with respect to the independent variables, right? So the gradient nabla f is given by partial f over partial x I plus partial f over partial y j plus partial f over partial z k, if we have a function of three variables, that is if we are considering three dimensions, that is x, y, z. But if we have a function of two variables only, then partial f over partial xi plus partial f over partial yj gives the gradient of the function, right? So the gradient is just a vector. It is a vector that is pointing perpendicular to the plane that is tangent at some point, right? So we can see this For instance, if we have a function, let's say we have a surface, this is the surface, for instance. All right, so this is our surface, and let's say some function f is defining the surface. So this is the surface we have. We can just color it, so it looks like a three-dimensional surface, right? So for instance, if we are interested in finding the finding the gradient at this point, so it means that the plane that is tangent to this point, a plane that is tangent to this point, having the vector perpendicular to the plane from this point, let's say we have a perpendicular vector pointing outwards perpendicular to the plane, that is making 90 degrees with the plane. So this vector is the gradient vector, right? Now to compute the gradient, we need to find the partial and derivatives of the function with respect to the given independent variables, right? Now we know that how to find the derivative. So if we want to find the partial f with respect to x, we are going to get negative 4x, and partial f with respect to y, we are going to get negative 2y. So the gradient of the function is negative 4xi minus 2yj. Now we are given a point that is 1, 1, so we need to compute the gradient at this point. So we need to just plug in the values. So x is 1 minus 2 times y is also 1, so it's 1j, right? So the gradient at this point is negative 4i minus 2j. All right. Now this is the gradient at this point. Now we need to find the direction vector. So the information that is given is that we need to find the directional derivative in the direction of the vector that makes an angle pi over 3 with the positive x-axis, so it's pi over 3. So we know that the vector will be just u equals to cosine pi over 3i plus sine pi over 3j. So cosine is the x component and sine is the y component, right? So in this manner, we will get the direction vector that will be 1 over 2i plus root 3 over 2j. So this is the direction vector. Now, this is a unit vector in the direction of the unit vector. Okay, so this is the unit vector. Since its magnitude is 1, we know that the magnitude is half squared plus root 3 over 2 squared. So if we sum this thing, we will get that is equals to 1, right? So the magnitude is 1. It means that this is a unit vector. Now we have the gradient at the point, we have the unit vector. Now we need to find the dot product of these two vectors, that is the gradient vector and the unit vector. So we will get the directional derivative. So nabla fp dotted with this unit vector u is equals to negative 4i minus 2j dot 1 over 2i plus root 3 over 2j. So we get negative 2 and negative root 3. So this is the magnitude of this directional derivative, right? So this shows the rate of change in this direction at this point, at the given point in the direction vector that is given as this vector making angle pi by 3 with his positive x-axis, right? So this is how we compute the directional derivatives. Now let's take one more example. Now we will see how to compute this for more than two variables. So let's find some example. Now here's an example, and more specifically it's an application. So the question is asking that suppose a point charge q is located at the origin of three-dimensional coordinate system. This charge produces an electric potential V involves given by the function. So it's a three variable function. We have x, y, and z. Now in the question they're asking that find the rate of change of the potential at this point in the direction of this vector, right? Now, first of all, we need to find the gradient, right? So by definition, we know that the gradient is this vector that is partial f over partial xi plus partial f over partial yj plus partial f over partial zk, right? This vector. So if we compute this partial, now f is given by this v, right? So we need to find the nabla v. All right, so it's simply partial v over partial x, partial v over partial y, and partial v over partial z. So this vector gives the gradient. So with respect to x, if we differentiate this function partially, we are going to get this partial v over partial x, this function that is negative k qx over x squared plus y squared plus z squared raised to the power 3 over 2. Similarly, for partial v or partial y, we get this function, this one here, and for partial v over partial z, we get this function. Now, we have this gradient vector, so we need to find the gradient at the point. So the points are given, point is given, that is 1, 2, 3. We need to plug in the values of 1, 2, and 3 in the corresponding variables x, y, and z in this gradient vector, given by the sum of all three vectors with the unit directions. So we need to plug in this 1, 2, 3, the point, and these values here, and we will get a vector in terms of constants, right? So here we can see that now the gradient at this point, gradient at the point 1 to 3 is given by this vector, that is kq, negative kq over 14 power 3 over 2 times I plus 2j plus 3k. Now the unit vector that is given, the vector that is given in whose direction we need to find the directional derivative is given as v equals to 2i plus j minus 2k. So this is given in the question. Now we need to find the unit vector first. So we know that the definition of unit vector is the vector divided by its magnitude. So the magnitude of this vector is 4 plus 1 plus 4, that is square root of 9. So we get 2 over 3 and 1 over 3, negative 2 over 3. So this is the unit vector. Now we have the unit vector, we have the gradient at the point. So now we need to just find the dot product of this gradient at this point and the unit vector. So because we are finding the directional derivative, that is the gradient in the direction of this vector, right? So we need to find the dot product. Now if we dot this these two vectors, so we will get the gradient at the point, so directional derivative as the square root of 14 kq over 294. So this is the potential, right? So this is the potential at the point increasing with this rate, right? So this is how we can compute this directional derivatives. So we just need two things, that is the gradient vector at the point and the unit vector, and whose direction we are going to find the directional derivative. So I hope you guys understand this lesson. So thanks for watching the lesson. That's all for the time being. In the next lesson, we will uh, see how to compute the equations of normal planes and sorry, tangent planes and normal lines.